So we want to discuss the concept of state functions and path functions. In thermodynamics, we have thermodynamic properties, things like pressure, temperature, energy, heat. All of those properties are either going to be considered state functions or path functions. The major difference is whether it matters how you get from point A to point B. State function is something that is path independent. In other words, it doesn't matter how you get from point A to point B. It just matters that you have a point A and a point B, and we don't care what happens in between them. We usually use capital letters for state functions like P for pressure, T for temperature. Those are state functions, and that it doesn't matter what happens if the pressure of a system changes, but the initial pressure and the final pressure are exactly the same. We say that the change in pressure is zero. It doesn't matter that it changed over the course of a process. It just matters what it was at the beginning and what it was at the end. A path function, on the other hand, is dependent on how you get from point A to point B. It's path dependent. And so we use lowercase letters to represent path functions, like little q for heat. The amount of heat involved in a change is dependent on the path. We have in thermodynamics some laws, and the first law of thermodynamics is that energy is neither created nor destroyed. It just changes form. You've heard that before in the law of conservation of matter and energy. And this is part of that law. And that means that whether we have the potential energy of position, or we transform that energy into motion, or we transform that energy of motion into heat or work, it's all the same amount of energy. The energy in the universe is constant. Another way of saying this is that all processes in the universe are accompanied by a change in energy. And so we use delta E. E is internal energy, the overall energy of a system. Delta E, therefore, is the change in energy of that system. E, you'll notice, is a capital letter, so energy must be a state function. In other words, it doesn't matter how we get from point A to point B, just that we have a point A and a point B, and we can find the difference in between those. Now, in chemistry, we talk about internal energy as being the sum of heat plus work. Q being the heat absorbed or emitted, either it's end or exothermic, and work is either done by the system on the surroundings or by the surroundings on the system. Together, heat and work make internal energy. Now, to give you an example of what we're talking about, when we take, for example, a plastic bag, we put some dry ice in there, and dry ice is just solid carbon dioxide. As the dry ice sublimes, it turns directly into a gas. It's going to cause the bag to inflate. Now, we can use that inflating bag to do something. For example, we can use it to lift a textbook. So if we want to take a look at this particular situation, figure out what is the system, what are the surroundings. Well, remember that we define the system. So we're going to call the system this expanding gas, perhaps the bag that encloses it as well. So the surroundings, therefore, are what is in direct contact, well, the air around it, and in particular this book. So do we have work done by the system on the surroundings, or work done by the surroundings on the system? And it's very simple. In chemistry, we're dealing with pressure and volume work, and we say that if the system expands, it's pushing on the surroundings, and therefore it's doing work. And if the system contracts, that means that the outside, the surroundings, the environment, the atmosphere, if you will, is pushing on the system, is doing work on the system. Okay? So we use signs just like we use for Q. Remember that when Q is negative, the heat is coming out. It's being exothermic. It's going into surroundings. And when Q is positive, it's endothermic. It's going into the system. Well, the same thing with work. If work is less than zero, in other words, if work has a negative sign, we say that work is done by the system. The work is coming out of the system. The system is expanding, and vice versa. Okay? Now, E is a state function, which means that you have an internal energy before a process, you have an internal energy at the end of a process, and it doesn't matter what happened in the process, but we just don't want to know the difference between those two. But E is made of heat and work, and both of those are path functions, meaning it is important what happens between points A and B. So there's a relationship between state functions and path functions. The path functions, the path is important. A state function, not so much. And we'll see that sometimes we can use one or the other to get what we need. In chemistry, again, work is pressure volume work. P is pressure, V is volume, pressure times volume, Boyle's law. They're indirectly proportional. So if we say that work is the change in pressure and volume, we could use this expression W equals negative delta PV. And if we distribute the negative delta over, we get work is equal to negative P delta V minus V delta P. Okay? So in other words, work contains pressure and a change in volume, also a volume term and a change in pressure. But that's too much going on. So we often talk about work at constant pressure or constant volume. If we can keep the pressure of a system constant, then delta P is 0. And if delta P is 0, then that whole V delta P term is also 0, and work is just the first term, negative P delta V. But if we can keep the volume constant, in other words, we do this in a container that has a fixed volume, then delta V becomes 0. And we can eliminate the entire term that has delta V, and we just get work is equal to negative V delta P. So doing a particular process at constant pressure or at constant volume, you can't have both. Pick one. It simplifies the term, the work term, very easily. And oftentimes we just want to know what the sign of work is in order to figure out what's going to happen to our internal energy. Okay, so here's a sort of a summary. We know that if Q is positive, we say that heat is transferred to the system from the surroundings, endothermic, and the effect on E, it will increase the internal energy of the system. That should make sense. We're putting heat into the system, so the internal energy E of the system should go up, right? If Q is negative, then heat is coming out, and that means that our value of D should go down. Delta E should be going down. Similarly with work. If work is done on the system by the surroundings, in other words, the surroundings are pushing it or compressing the system, then that's going to give W a positive value, and it's going to increase our internal energy. And likewise, if we let the system expand, it does work on the surroundings. W is negative, and that should decrease the amount of energy in a system. So knowing the signs Q and W and knowing how big they are can tell you the overall effect on E. All right, so we're going to take a look at energy processes within a phase and between phases. And this is just basic calorimetry, for example, calculations using Q, M, delta T, and all of that we already know how to do. So for example, if we want to take a look at how much heat is absorbed when 10 grams of water are heated from 20 degrees Celsius to 25 degrees Celsius, we just use Q equals M times C times delta T. Where the M is 10 grams, the specific heat of water is 4.184 joules per gram degree Celsius, and the delta T, the change in temperature final minus initial, is 5 degrees. Q is positive, 210 joules. Easy. Now, what about between phases? What if we want to talk about how much heat is involved in melting or boiling? All right. So here's an example. How much heat is needed to completely vaporize 10 grams of water at the boiling point? And we have this information, this thing called heat of vaporization. The heat of vaporization is the amount of heat necessary in kilojoules to vaporize a mole of water. It's in kilojoules per mole. We have 10 grams of water, so we're first going to convert the 10 grams into moles by dividing by the molar mass. And then we're just going to multiply by the heat of vaporization, 40.65 kilojoules per mole. It takes 22.6 kilojoules of heat to turn 10 grams of water into steam at its boiling point. Now notice, we can't use Q equals M times C times delta T. And the reason we can't use Q equals M times C times delta T here is because of a peculiar thing that happens when a substance undergoes a phase change. Whenever a substance undergoes a phase change, and this is really important, the temperature does not change for the entire time that it takes that substance to make the complete phase change. So when water is going from liquid to vapor, it's boiling, the temperature of that water stays exactly at 100 degrees, as long as we're at sea level, and it stays at 100 degrees until the entire amount of water is converted completely to steam. So if you use Q equals M times Cp times delta T is 0 during a phase change, you get Q equals 0. But that's silly. Of course you have to add heat to get water to vaporize. So Q equals 0 is not accurate. And so when we're changing phases, when we're going from one phase to another, one physical state to another, we have to use a different process. And we're going to use either the heat of vaporization when we're vaporizing, or something called the heat of fusion when we're melting. We'll see that in a minute. Okay? So let's say that we want to take a look at the total amount of heat absorbed when we go from ice below zero all the way up to steam at above zero. Now there's 5 different things we have to do. We have to calculate the amount of heat necessary to raise the temperature of ice from whatever it's at below zero up to the melting point, zero. Then we have to calculate the amount of heat necessary to melt that amount of ice. That's the heat of fusion. Then we have to calculate the amount of heat necessary to raise the temperature of the liquid water now from zero all the way up to its boiling point, 100 degrees. Well, that's Q equals mCp delta T. Then we have to calculate the amount of heat necessary to boil, to convert all of that water over to steam. Well, that's the heat of vaporization again. And then finally we have to calculate the amount of heat necessary to raise the temperature of steam from 100 degrees up to wherever we want to be. That's 5 different little calculations. 3 of them, the ones that are within a phase, the first one, the third one, and the 5th one, are all done with the traditional Q equals M times Cp times delta T. 2 of them, the ones that occur on the horizontals here, the phase change, those are going to be done by multiplying the number of moles of substance times the heat of fusion for melting or the heat of vaporization for boiling. So if you want to be real fancy about it, you can use this equation. Q total is equal to the sum, or I equals 1 to 5, there are 5 different things, the sum of the Q values for I. Let's take a real example. Here's the example. How much total heat is needed to raise the temperature of 100 grams of water from negative 15 degrees Celsius up to 125 degrees Celsius? If it were at negative 15, we're going to be solid ice. All the way up at 125, that's greater than 100 degrees, that's going to be steam. Now here's some data that you're going to need. These are some constants. The heats of vaporization and fusion are given. We already know the heat of vaporization of water is 40.65. It's different for every substance. The heat of fusion, the amount of heat necessary to melt 1 mole of water, is 6.01 kilojoules. You might want to think about this for a minute. How come it takes so much more energy to boil a mole of water than it does just to melt a mole of solid water to liquid? How come it's so much more energy to boil it than there is to melt it? Similarly, if we look back at our diagram here, why is the boiling line so long? Look how much heat we have to enter to get it to boil compared to the amount that we needed to melt. Think about that a little bit. You should know the answer to this. All right. A couple of other things that I want to point out before you try this problem is that the specific heat capacities here are given in joules per mole times degrees Celsius. You're used to using, for example, the specific heat of liquid water as 4.184 joules per gram degrees Celsius. Well, in this little table at the bottom, it clearly says that the specific heat of liquid water is 75.35 joules per mole degrees Celsius. And you'll notice I put it down there also as the traditional value. But these values are in joules per mole. So we're going to be working in moles. We have 10 grams of water. We're going to be working in moles. I want you to stop the video and I want you to see if you can figure out all 5 values of Q and then add them all together to get Q total. Stop the video and try it. All set? Let's see if you got what I got. So for Q1, this is the within a phase, within the ice phase, we had to raise the temperature from minus 15 up to 0. I got 3.09 kilojoules for that 10 grams. 10 grams is about 5.55 moles. For Q2, that's the fusion, that's the melting, 33.4 kilojoules. That's the number of moles times the 6.01 kilojoules per mole. For Q3, that's raising the temperature of 0 degree water all the way up to 100 degree water, so delta T is 100 degrees. The specific heat was given for liquid water at 75.35, and again we start with moles. And that came out to be 2.32 kilojoules. Then Q4, that's the amount of heat needed to boil this 100 grams. So moles times the 40.65 kilojoules per mole. 225.6. That's the most heat in this entire thing was needed just to boil the water. Again, think about why that is. And finally, Q5 is to raise the temperature from 100 degrees up to 125 degrees, and that's 4.66. We add them all up, we get 269.1 kilojoules. That's the total amount of heat necessary to raise the temperature of 10 grams of water from negative 15 degrees Celsius all the way up to 125 degrees Celsius. It's pretty simple. It doesn't take very much, but you do need those values listed at the top of the screen right now. All right, so go back, watch the video, make sure you've tried this example on your own, and we'll continue with the next time.